the Achievers Gathering with the sole aim of making popular the use of R in Africa, at the same time increasing the analytical skills of every young Africans. To do this, we have carefully selected well-trained data specialists and analysts all across Africa who will be doing justice to the topic we have earmarked for this particular training. And the one of them will be speaking to us today, and it's no other person than Mr. John Bagiliko. The other person is Mr. Kofi Doji Nomovi, and the third speaker we'll be having for AREFOR'20 is Mr. Martin Bagaram, and the last speaker we'll be having for AREFOR'20 is Mr. Folajimi Aroloye. We now have a very, very important personality who will be giving us the keynote address. That is, immediately after we have John, we'll be having Mr. Dixon Nkwantabisa all the way from the United States. They will be joining us to give us a brief keynote address on the need for a technological revolution in Africa. And that will be coming up immediately after the section of Mr. John Nkwantabisa, Mr. John Bagiliko. So one of the rules, let me quickly share with us the rules we'll be having for today's training. The first rules is that everybody will be muted until the question and answer segment. And if there are noises on your background, please, I will plead with you to please move away from those noises so that we can all get to enjoy this training and get to hear ourselves very well, so that we will not give the trainer much stress to pass across what he has prepared for us. At the same time, I also want to encourage us to please make use of the chat room. I won't be doing any of the teaching. I will just be available on the chat room and attending to any of our questions or opinions or feelings, at the same time directing it to the trainer for today. So I'm going to share with us a brief citation about our trainer for today, Mr. John Bagiliko. I'm going to share with us his brief okay. So we have Mr. John Bagiliko. So Mr. John Bagiliko is a data science and software engineering consultant at Superfluid Labs, Ghana, and a product of the African Institute of Mathematical Sciences, Senegal, where he obtained a master's degree in mathematical sciences, big data, and computer security. He has successfully undergone training in data science with Microsoft Professional Program. He's passionate about mathematics and the use of technology to solve real-world problems. He is the team lead of AI Ghana and the Zindi country ambassador for Ghana. So today we are pleased to have with us Mr. John Bagiliko, who will be taking us through the overview of regression. In the next few hours, he will be taking us through that topic. And I want you to sit down, get your, R Studio ready on your system, and get to enjoy what he has prepared for us. I know we can't put our hands together where we are right now, but I want us to welcome Mr. John Bagiliko for his section. Thank you.
Hi, everyone. Thank you, Joshua, for the flattery kind of introduction. And to everyone, I'm glad to be with you. And thank you for joining this event this year. So without much ado, I will just share my screen and then we'll start. Joshua, you let me know if you can see my screen.
Okay, yeah, we can see it.
Okay. Okay, I'm not able to see the screen. Okay, cool. I can see now. Is it okay for you?
Yeah, it's okay.
The font.
Yes,
Is
it's
it
okay. Yeah, it's okay.
okay? So today I will be looking at the overview of regression with you guys. Um, I hope we all enjoy this section. If you do have questions along the way, you can put it in the chat section, as Joshua said, and I'm sure he can let me know directly. I don't mind if you interrupt during the section, so I can just answer and we'll all be clear and move on. So, who is John Bagiliko? Well, Joshua has already kind of introduced me, so there's no kind of need to do this again. So what is regression? Um, so from Investopedia's site, they define regression as the statistical method used in finance, investing, and other disciplines that attempts to determine the strength and character of the relationship between one dependent variable, y, and a series of other variables. Okay. Sorry, I would have to mute myself in the background. Something. Sorry, let me attend to. Sorry for that. There were some background noises, so I had to check that. Okay, I'm sharing the screen again. Joshua, can you see? Sorry for the interruption.
Yeah.
Okay, sure. So that is the definition from Investopedia. So kind of what is being said here is that we try to determine the relationship between one independent variable or multiple independent variables and a dependent variable. Okay. So regression is broadly classified or categorized into two. So we have linear regression, which is also subdivided into simple linear regression and multiple linear regression. By the way, if it's too basic for you, I'm sorry, but I try to kind of cover in such a way that the basic participant, I mean, then someone who is new to regression would still get it. So if you are an advanced kind of master, pardon us because you're all trying to understand it. And then we have nonlinear regression. Okay. Okay. So what is simple linear regression? In simple linear regression, the idea is what to predict the dependent variable using only one independent variable, and the main always to fit a line in the data points, best fit line. Hello, Joshua.
Yeah, we can hear you.
Okay, I'm not able to see myself, so I don't know how.
So just go ahead, we can hear you.
Cool. So the x in this case is now a independent variable. The y being a
Guys,
dependent variable.
sorry, it's Kofi here. Can you hear me?
Yeah, Kofi, I can hear you.
Okay, I'm sorry to interrupt, but I would like to tell you to check the chat because some people are asking John to be more audible because they cannot hear him.
Oh,
Okay, John, please, can you be more audible, please? Yeah, thank you, Mr. Kofi.
You're welcome.
sure. Okay, I think I'm able to. Okay. Am I audible now? Can you hear me?
Yeah.
Okay. So, as I was saying, x is our independent variable, y a dependent variable. Then, in this case, what we are trying to compute is the m and c, with m being a gradient, the gradient of the best fit line, and c the intercept. We'll get to the meaning of those. Let's look at an example. So here, suppose that we want to know the relationship between the number of years of experience at work, per se, and salary. We want to know if there's a relationship between these two variables. So what we try to do is to fit a line of this nature, which is of the form mx plus c, and c is our intercept. Sorry, if I could just put this somewhere. Okay, cool. Sorry for that. Okay. So C being our intercept, and I would show you what it means and where to find C. So C would be kind of asking, what is the salary of someone with no or 0 years of experience? So here, all we do is that as you go along the x-axis, you also look for the corresponding value on the y-axis. So here, what they see is telling us is that if somebody has 0 years of experience, what would be the salary, kind of. So in that case, you count it here. And so from there, then we move forward. So any number of years of experience will have a corresponding salary. Okay, good. So the objective of this whole process is to kind of, so as I mentioned, this is the fitted line. We fitted this one. So we are trying to kind of minimize the error between the point that you fit and the actual observed value. So kind of try to reduce the distances between the observed value and the actual fitted line. So we want to get the minimum, the sum of the errors. So the fitted point minus the observed point for each of these points we are seeing here, and then we sum those differences and square, and then dividing that by n. So that's finding the mean of the of all the errors, and then we want to get the minimum value as possible. So we will be fitting multiple lines of this nature. So we can fit another one like this or that way, just to compute the MSC and see which one gives us the smallest value possible. Okay. Joshua, let me know if there are any questions at this moment.
Okay, no, there are no questions. You can move on.
Okay. Now, so that is it for simple linear regression. Since it's one variable, we are able to kind of plot it and see. And as we can see, the line is of the form y is equal to mx plus c. But when we come to multiple linear regression, it is also a linear combination kind of, where you have multiple independent variables, x1, x2, up to xn. Still, you have your intercept there, kind of, and then the gradient. So each of the independent variables has a gradient. So the objective hasn't changed, only that the variables have increased. Okay, so we try to still optimize. After we predict y, we still want to minimize the error between the observed value and the predicted value, as I've already mentioned. So the objective is still the same, except that the number of independent variables have increased in this case. Okay, so in this case, Mn would be the gradient of the nth independent variable, and C still remains the same. It's a constant, but we try to look for C and then the Mn's. Okay. Now, so two independent variables form a plane. Okay. When we had one independent variable, we were fitting a line. Okay. Now, if you have two independent variables, what you'd be fitting is a plane. And if you have three or more independent variables, you would be fitting a hyperplane, which in this case is difficult to plot. Even with the plane, well, you could do that. But if the independent variables increase.
Hello.
Hi.
No, go ahead. Go ahead, Mr. John.
Okay. If the independent variables increase to, let's say, 10, then you have a hyperplane that, well, it's going to be difficult to plot that or visualize. So the objective is the same as the the simple linear regression. After you predict, you try to minimize the error between the observed value and the predicted value, okay? So that the sum of the squares or the mean of the square of the errors is the minimum. Okay. And then we come to the nonlinear regression. Probably let me go back, and as you can see here, we have a relationship which is kind of linear, because this is a linear combination, kind of. So this is why we call it linear regression. Okay, when you look at the simple linear, it also has, it's also in a linear form. Okay, this is already the equation of a line, so we all know that it is linear. And this one is a linear combination, so it's of course linear. Now, coming back to the nonlinear regression, an example can be the power equation. Okay, if you have some data points, and for instance, let's use this. So this was plotted from, I will show you this where I generated this from later. But we have some data points of time and heart rate, okay? And when we plot it, we see it's in this form, okay? Now, suppose you want to fit a straight line kind of this way. Well, you can estimate some things and get close, but it would be better if you are able to fit some kind of curvy line. That would tend to work better rather than fitting a straight line, which would ignore values either beneath or above. So the power equation is one of those you can fit to data, and you see that it's already curvy. We can also have the Weibull growth curve. It's also not linear, as you can see. This is not a linear combination of some y and x's. Okay, it's non-linear. And usually for the non-linear regression, it's mostly fitted by kind of experimentation. So you have to tune and just experiment until you arrive at what you want. Then we also have the Fourier equation, which you can also see. So if you have data points that kind of tend to have this shape, then the best function you can fit to it would be the Fourier kind of equation. So the multiple, or there are uncountable nonlinear functions you can fit to your data. But like I said, it all always have to be kind of experimentation. And this is advanced. Usually the linear regression works, even though, well, sometimes we have to use the nonlinear just to kind of take care of some other parts. For instance, population growth. Okay, if you are fitting a line for population, the population growth with respect to time, we all know that it is not linear. Population growth is not kind of linear because people die. So at a certain age, people tend to die. So it's not like, okay, if you are fitting a line for population growth, then you can fit it. So if you are fitting a line for population growth, then you can fit it. So if you are fitting a line for time growth, then you can fit it. So this is as the time increases, then population will continue to increase and will never drop. So this kind of situation, you may not want to fit a straight line to search an instance. So you have to kind of look for a better function to fit to that kind of data. Okay. So like I already said, it's mostly experimentally determined. So you'd have to kind of experiment to see which nonlinear function would kind of work for the data that you have. And sorry for that. And like I already mentioned, the objective is always the same in regression. We try to minimize the error as much as we can. We get the, the function that gives us the least error between the predicted and the observed values. Okay. How do we then evaluate a regression model? So the three most common evaluation metrics for regression tasks are the following. We have the mean absolute error. So throughout my talk, I was talking about the mean squared error, but we have the mean absolute error, which is computed by finding the absolute value of the difference between the predicted and the observed divided by the number of observations. We already talked about the mean squared error, and we also have the root mean squared error, also given by this formula. So the objective is the same, to kind of minimize these. Cool. Now, how do we know our model is a best fit for our data? So you have a data, you fit a model. How do you know that it works? Okay, these are some things you can look out for when after you fit your regression model. You can check these to kind of have the confidence that, okay, it works. One of them is the R squared, which we would see when we do the practicals. The higher, the better for R squared, maybe greater than 0.7. And when I share this slide, you kind of be able to look at the source. Sorry. We also have the adjusted R squared. Also, the higher, the better. So this is good if you are comparing multiple models. Okay. Suppose you have two models and you want to pick which one is better. Then of course, the one with the higher R squared would be better. You know. Also have the F statistic, which is also the same. The higher, the better. The standard error, closer to 0, the better. T statistics, this should be greater than 1.96 for p-value to be less than 0.05, and so on and so forth. Okay. So what's the importance of regression? Well, apart from we being able to discern information from data, we're able to understand other patterns that could arise, because after you fit your model, you're able to kind of know which variables played much role in it, so doing this help you unpack some hidden patterns in your data. And in as much as your data to kind of predict some, also help you to kind of
Oh, hello? Hello?
did I drop off?
Okay, good.
Hello?
John, can you go ahead, please? We are with you.
Yeah, hi. I think I dropped off. Sorry for that. I don't know what happened. Okay. Can you see my screen again?
Yes, yes.
Okay. So these are some of the importance of regression. I'm sure that there are many of them you can find in multiple fields. Yeah. So thank you very much. So we would then go into the practicals. We would